Okay, so welcome back everyone to the second half of the lecture this morning. And thank you again for all the good questions, and please do keep them coming. So what I was going to add to the thermalisation story is the question of entropy growth. And this is connected to things, of course, that Steve was talking about yesterday. And so the other thing we kind of expect here is that if I have a system and I have a look at sort of a particular region, kind of A, and say the rest of the system is B, then the other thing I kind of always expect when a system thermalizes is that somehow the entropy becomes proportional to the volume. So we expect the entropy in a system to be extensive, to be proportional to the size of the volume. Now, entropy here, normally what I would do is I would take a density operator for the system, and I would say that, the entropy is the trace of rho log rho, where the logarithm is taken to your favorite base. If you're a computer scientist or you're working with digital quantum computing, you'll take a log to the base 2. If you're doing statistical mechanics, you'll take a log to the base e. It doesn't really matter. And so here, you will ask now, though, again, if I've just evolved my pure state, I've got a psi of t, then my rho, the density operator describing the system, is an object like this. Who has seen density operators before? Okay, who's not seen density operators before? Okay, that's very helpful. So this, of course, is a pure state, and trace of rho log rho will, of course, S of this, okay, is 0. So there's no entropy. It's a pure state, okay? So what does this correspond to? Well, this corresponds to the fact that as this thermalizes, if I look at one part of the system and I take rho A, which is a trace over B of the rho for the whole system, and this is, of course, very reminiscent now of exactly what Steve was doing yesterday, then what I can do is I can ask, what is the entropy of sort of part A of the system, which is the trace of rho A log rho A. I should have put minus signs, shouldn't I have? If I make a sort of typo on the board, then please remind me. This is minus trace of rho log rho, right? Good. So the point is that this then is what you would expect to grow to the point where this whole thing sort of looks like a volume law. So if I take the sort of size of this thing, and I call the size of this thing sort of like modulus A, it sort of is the size of A, then what I kind of expect is this, that as I thermalize, that if I ask what sort of S of A is as a function of the size of A, where this is sort of the whole size of the system, okay, so this is kind of A plus B, okay, then I expect to get this kind of linear dependence up here. And I also similarly, once I get past the midpoint of the system, I expect to have this sort of, again, decay, go down. And so I expect to have some sort of a curve like this, where at least when A is much smaller than the whole size of the system, that I get this linear relationship between the entropy and the size of that block. That's quite different to what happens if I go to the ground state of a one-dimensional system, for example, and I ask now, what is the entanglement entropy here? And precisely the thing that makes DMRG work the way that Steve showed you yesterday is that instead of this sort of so-called volume law, okay, where the entropy depends on the system size in that way, you get instead what we would call an area law. I shall write it big enough so that you can actually read it. This is an area law, and basically what that tells, so it's called an area law because it's the size, it goes to the size of the boundary of part A of the system. Now in a 1D system, the boundary is of a fixed size, okay? As you extend the size of A, the size of the boundary doesn't change in 1D, and so you expect this to saturate. And this area law is kind of the theory behind why, especially for gapped 1D systems, but in general for 1D systems in the ground state, you find that DMRG works so well. So this is sort of what you expect, this kind of thermalization. And of course, you can describe this with all of the power of the sort of Schmidt decompositions and singular value decompositions that Steve showed you yesterday. In the interest of time, I'm going to sort of skip that sort of slightly, but really to also kind of double down on the fact that in this way, thermalization is also building up entanglement between different parts of the system, okay? And this corresponds very closely with another idea, which is the idea of scrambling. So when we talk about scrambling of quantum information, the idea kind of is this: if I've got a whole lot of, if I've got a whole sort of spin system, and I've got sort of information on this sort of spin in the middle of the system, then the dynamics that sort of would thermalize the system after a quench would sort of take this information and kind of spread it over all of the different degrees of freedom that I could have within my system. And so the idea of scrambling is essentially that I'm spreading quantum information. The spreading quantum information, and I'm developing bipartite entanglement across all possible partitions. And so the idea of sort of scrambling is that essentially all of the different possible bipartitions that you have in a properly scrambled state should essentially get to the point where the entanglement entropy saturates to a curve that has this volume law, but it's a special version of it where ultimately, if you properly scramble the state, you would expect to get to the extreme version of this, where essentially you get to the point where the entropy is as large as it would be if you took a random quantum state. Okay, and if you take a random many-body quantum state and you ask what this looks like, then on average it will go to this type of volume law curve, but in the particular quantitative amount, it's a so-called Page curve. And this comes from a really nice paper from back in the 1990s by Don Page. So this was in PRL. This is references 71, 1291, if I'm reading my writing correctly, 1993. And essentially what Don Page did is he asked, what is the entanglement entropy that you would expect if you have a random quantum state? A lot of this was, again, inspired at the time by thinking about information paradoxes in black holes. And there was a lot of things that sort of that happened sort of after that that connected into it. Now, scrambling has a number of connections. And you might say, well, what's the difference between scrambling and thermalization? Thermalization is a very general thing, which you can think about also in terms of the system relaxing in contact with a heat bath, connecting to the reservoir. Scrambling is really about unitary quantum dynamics generally that are building up entanglement and getting us to the point where the bipartite entanglement entropy sort of saturates this curve. And the connections of this, firstly, again, are similar a little bit to things that we would touch on with the eigenstate thermalization hypothesis, in that it connects to the question of chaos, or sort of signatures of chaos in quantum systems, or many-body quantum systems. And if we had another 3 lectures, we could talk about out-of-time order correlation functions, a connection to sort of semi-classical notions of chaos, which are a lot of fun. And then it also connects to the thing I've alluded to a few times, which is quantum information in black holes. And so there's a whole sort of community of people who worked on this at different points. Beautiful papers, for example, thinking about this by Hayden and Preskill back in 2007 in the Journal of High Energy Physics. So again, this is from a very different community. And then similar related things, sort of talking about fast scrambling by Cicino and Susskind. Again, J. Hip, 2008. Apologies a little bit for my writing, 065. But these are really interesting sort of connections to a different community. And there, again, what they're looking at is this fast scrambling regime, where you should be able to scramble in a time that grows only logarithmically with the system size. And of course, if you can build this, it's kind of interesting because you could also think about this as a fast encoder for quantum information. But one of the most important connections here, of course, is then a difficulty sort of in classical simulability. So what I'm going to do in terms of the classical simulability is just to remind you very briefly of what Steve presented yesterday. And for anyone who would otherwise try to furiously sort of scribble down what I have on the slides, I think there's a OneDrive for slides, is that right? So I will upload the slides to that so that you don't have to copy everything down, or I'll ask someone how I'm supposed to upload slides to that. But here, so this is basically what Steve was looking at yesterday. And of course, the matrix product states describe well your many-body state, so long as it's in some sense weakly entangled. And if you've got a bond dimension in your matrix product state here, which is D, so this is capital D by capital D matrices, okay, then this is able to represent an amount of entanglement up to a maximum value of the von Neumann entropy, which is the log of the dimension. Again, here if we're taking the von Neumann entropy as a logarithm to base 2, okay, that's where this logarithm to base 2 comes from. Okay. But what that means is that if we get a significant von Neumann entropy, that the dimension of the matrices has to increase. In particular, what this gives us, okay, this doesn't tell us here necessarily that if we have a sufficiently low von Neumann entropy, that we'll have necessarily an efficient representation in terms of matrix product states. In fact, there was beautiful work by Norbert Schuh and Ignatius Serac and a few other people in about 2008 that showed that actually the sufficient condition for representation as a matrix product state relies on a Rényi entropy of order 0, actually, which is really interesting. But this is the necessary condition, okay? So there's a sufficient condition in terms of Rényi entropies, but what you can certainly say is if the von Neumann entropy that you're trying to represent is too large, then you are not going to be able to represent this with a matrix product state. So here, if I tell you what the von Neumann entropy is, the minimum size of the matrix that I will need is the exponential of that. So if my von Neumann entropy grows linearly in time, then I need to have an exponential growth of the bond dimension in time to represent that. And of course, unfortunately for classical simulations, and fortunately for the usefulness of quantum computers in this domain, that's exactly what happens in typical out-of-equilibrium dynamics. And discussions of this go back to this work by Calabrese and Cardi, Journal of Statistical Mechanics in 2005. And actually, as Steve already alluded to yesterday, basically what's going on here is you're generating sort of local, so if you have quench dynamics, it generates local excitations, they propagate, and they propagate according to a Lieb-Robinson bound, okay, with some sort of typical maximum velocity. Over time, if I draw a dividing line between the two parts of the system, I'm having more and more of these excitations that kind of form in pairs, in correlated pairs, sort of crossing over this boundary in the middle. And what it leads to, and this was this result of the Calabrese and Cardi paper, is that in generic quench dynamics in any sort of size of system, that typically the von Neumann entropy will grow linearly in time. And that growing linearly in time means in general that when you're trying to use a matrix product state to describe this, that your bond dimension is going to have to grow exponentially in time. So there's going to be some time scale where you can do this with small system sizes, okay, or small matrix sizes, and then after that point, it's going to become exponentially difficult to go further in time. And so here, what we did was quench dynamics actually in the Bose-Hubbard model, going from the mod insulator into a superfluid parameter regime, and you see the increase of this. Now this is a calculation done with time-dependent DMRG, or with matrix product states basically, and this is now growing exponentially the size of the matrix product state, and you'll see down here they're all converged, okay, because they're all giving us the same values. But as I go up in time, you see that I have to go to higher and higher bond dimensions in the matrix. So this is 2 to the power of 9, so this is a 512 by 512 matrix. And you can see every time I increase this by a factor of 2, it only allows me to go a tiny bit further in time. Now, there are some specialized techniques you can use for some systems and how you contract your matrix product states that will get you an overall factor of 2 in some of these times. And as Steve said yesterday, when you're trying to do certain spin models, some things in the Heisenberg model, we can evolve up to about 20 times 1 over the coupling strength or so, or 30 times 1 over the coupling strength. Here for a Bose-Hubbard model, it's actually more like about 3 or 4 times 1 over the tunneling. Okay, so it's actually, so for a Bose-Hubbard model, it turns out to be much worse. But in any of these things, you always hit a wall where it becomes exponentially difficult. And this is essentially what I'm drawing here. Okay, at short times, the difficulty basically is not particularly concerning, because if I can do this with 500 by 500 matrices, I can do this on my laptop during the lecture. Okay, 200 by 200 maybe. But the point is that I eventually reach a point where I can't deal with this anymore. However, in principle, if we go out to thermalized states, you might find ways that you can use thermal calculations, okay, in quantum Monte Carlo techniques, or indeed sort of Monte Carlo based around matrix product states that might allow you to get to these types of things classically and work out what those thermalized states are going to be. But this intermediate regime becomes extremely difficult. And although you can come up with approximate methods for certain systems, at the moment, even in 2D, these sorts of matrix product state calculations are the best thing that we have to basically, from first principles, without uncontrolled approximations, to try to solve for dynamics in these systems. And of course, that gives us a beautiful regime where we can think about whether analog quantum simulators can give us values for quantities that you get in dynamics in this regime that we can't find, or that are exponentially expensive to find on a classical computer. Questions?
Yep. You mentioned that small Reynolds entropy of zeroth order is sufficient, and small von Neumann entropy is necessary.
Yep. Then
what would be the optimal measure or order of Reynolds entropy we should use when we're doing MPS in general?
So again, I'm going to give you a practical answer to this. Normally what we do is, of course, we just increase the bond dimension, or more often to do proper convergence, actually, we specify a cutoff where we're going to throw away Schmidt coefficients beyond, below a particular value, or squares of Schmidt coefficients beyond a particular value. And that gives us effectively a tolerance for the fidelity of a state that we get after we throw away some of the information relative to the state before we throw away the information. And then we do convergence in that. So, so where these things like the order zero Ring entropy become important is if you'd like to really look on a theoretical level at for which classes of states can you prove mathematically that matrix product states provide you an efficient representation. And so you can show for gapped spin models effectively that this will always provide you an efficient representation, and that was what was proven in this 2008 paper, and for that you had to go via the order zero Ring entropy. It's not something that I've actually ever calculated in a practical calculation. This is really much more for purposes of proofs. For calculating increase in entropy like this, sometimes we'll calculate the von Neumann entropy. Sometimes we'll be interested in Ring entropies. Ring entropies, instead of being minus trace of rho log rho, S Ring, okay, is then so the Ring entropy comes with different orders n, okay, and basically it is trace of log of the powers of the matrices. Have I written that correctly, or do I have a?
I think so. Yeah.
It's always hard when you're looking at it on the board. I'm like, I'm sure. Okay. So the point is it depends on powers of the density operator. Normally, this has all of the same sorts of qualitative behavior when you're looking at thermalization and things like that. But the beauty of it is that these are sorts of things that you can come up with crafty ways to measure in experiments. So Marcus Greiner, for example, and his group back in about 2009, 2010, no, it would have been a little bit later than that, maybe 2012, 2013, something like that, wrote several papers looking at things like thermalization and actually looking at the Ring entropy as a function of time and showing this, this saturation to a volume law for a small number of particles with bosons in an optical lattice. And there's a really cute technique that you can use that we had fun thinking about back in 2012, where you essentially interfere two copies of your state in order to work out sort of a Ring entropy of order 2. Mm-hmm. So I can say more about that if people are interested in the future. But yeah, so generally we're calculating either a von Neumann entropy or one of these Ring entropies because the Ring entropies are normally more straightforward to measure in an experiment.
And one quick additional question is, when you're drawing the up and downs of difficulty, is the late time dynamics has many entanglement but easy, or entropy or entanglement actually decreases as time evolves?
So if you write down sort of operator expressions for local sort of thermal density operators, then you expect the entanglement in the density operator representation at least to be lower. And what's a bit system dependent is whether or not this necessarily happens if you're looking at really a very specific sort of pure state evolution. The assumption here is you're going over to something where it doesn't matter exactly which initial pure state you had, so you get some advantage out of essentially being able to average over things down here.
Time average.
Or average over similar initial states, for example. Yeah. So that will normally particularly help. You normally can't, without doing something funny, actually evolve your codes just directly over to here without throwing away a whole lot of information and being very imprecise about where you're going. So you normally need to have a slightly different way of getting at this, but then you normally do have another way of getting at this classically. Another question over here.
So the bond dimension exponentially growing, that's true for strongly coupled 1D systems too, right?
Sorry?
The bond dimension exponentially growing with time should be true for strongly coupled 1D spin systems too.
Absolutely, yes. Yeah. So the exponential growth with time, this is assuming that you have quench dynamics. Normally the treatment here is in one dimension, but if you draw a sort of a boundary across a higher dimensional system, you'll see a very similar growth.
Thank you.
Other questions? Okay. So that brings us to here, okay? And so I should, I will just go ahead and we might have to speed up a little bit. We've already touched on the different bits and pieces of this. So now I want to talk about open quantum systems. And what am I going to do? I'm going to erase this bit and add the open quantum systems to the left-hand side of the board, because there are still elements of the quench dynamics up there that we're going to need, and there are elements of this I'm about to come back to. So open quantum systems are lots and lots of fun. At least I'm a quantum optics theorist, and so I like systems coupled to their environments. Why do I like systems coupled to their environments? Well, firstly, why don't I start with why should I not like a system coupled to its environment? Sorry? Oh, well, what's worse is it will thermalize to the temperature of the environment. But yes, experimentalists, do you like coupling to the environment? Or do you spend most of your lives trying to get your ions not to talk to their environment? Right, so that's why I might not like coupling to the environment. Right, why do I like coupling to the environment? Because it's inevitable, and I want to talk about real physical systems. And in fact, that's going to be most of what I'm going to talk about today. I'm going to talk about modeling the thing that is inevitable anyway. Yep, so you're absolutely right. But in my case, it goes beyond that. I actually really like coupling to the environment. So why do I like quantum systems coupled to their environment so much? Sorry? I want to control them. I want to measure them as well. And of course, I can't measure them if I can't couple them to the environment. But that almost falls under the category of it's inevitable. Ion trappers. You know, why do you like coupling to the environment before you do most of your experiments? Yeah, in your particular case, you play with some really nice mid-circuit measurements, and so yeah, that's true. Sorry? Exactly. Okay, because you want to start with things that are cold. And in quantum optics, we know that if you tailor the coupling to the environment, then you can do a whole lot of things that if they're not carefully controlled would lead to lots of heating, and that it makes things incredibly cold. So scattering laser light off atoms or ions in a very controlled way suddenly makes these incredibly cold systems if you just couple in exactly the right way to your environment. And this is the beauty in quantum optics, that we can describe microscopically very well, again from first principles, what's happening between the system and the environment. So we've got a system, and it couples to its environment. And what's beautiful about quantum optics, and the reason why we've loved coupling to the environment for so long, is because if I have these sort of couplings to the excited state with sort of, omega x, this is a laser now driving a transition from the ground to the excited state. I've got some detuning. I should think about the fact that I have an optical frequency here. I might call it omega naught. And in principle, I've got this thing that you might think I'd rather not have, which is a spontaneous decay gamma. Okay? So I've got the scale gamma for this coupling between the system and the environment. I've got this kind of omega naught in the system timescales, which is this optical frequency, which is normally 10 to the 14 hertz. And then I've got this kind of omega, this coupling via a laser from the ground state to the excited state. I've got a detuning, and these types of things. And what is beautiful in quantum optics is that this gamma Typical decay lifetimes of alkali atoms or ions with single electrons. Right, microseconds. Okay, these are megahertz scales. Typical omegas. Sorry? Megahertz to gigahertz. You drive this with a really strong laser, we might get sort of tens of gigahertz and things like that. These things, delta's a bit funny. You can make it small, you can make it large. In the early days, this tended also to be of the order of gigahertz. If delta gets a little bit large and we want to do things very far tuned, we can adapt for that. But generally, these are all 10 to the 6 to at the most kind of 10 to the 9. And this beautiful frequency scale, omega naught, is an optical photon. Optical photon frequency. Right, so normally actually for visible light around 10 to the 14 hertz. And so all of a sudden, if I want to do perturbation theory in these parameters relative to this, my perturbation theory is good to about 6 or 7 orders of magnitude. And so now as a quantum optics theorist, I'm totally in business. And so what I can do is I can do perturbation theory effectively in the coupling of the system to the environment. I can then, of course, the other thing is the environment doesn't sort of think much about my photon. My photon actually disappears pretty quickly. And what's the relevant ratio of timescales for how fast the sort of the photon flies away? If I've got an atom and it emits the photon, can I make the same argument about how fast the bath relaxes? So how fast does the photon fly away from the atom? Sorry? Nanoseconds? I would say it's faster, actually. Okay, what's the speed with which the photon flies away from the atoms? It's the speed of light, right? Okay, because it's a photon, right? And how far does it have to move away from the atom before I can say it's left and this environment is basically a vacuum again? How far does it have to go? Sorry? Angstroms? So the challenge with angstroms, which would be fantastic, because if it only has to move away by angstroms, then it's going to be really, really fast. Okay? It's a little bit more challenging than that because I have to ask what the relevant length scales are actually in the problem. And when I think about the photon wave packet going out, there are length scales associated with that propagation that I'm going to have to worry about a little bit. In fact, in atomic physics, we're using a dipole approximation here. So I've assumed that the atom is point size, so I don't have a size of the atom in my problem, which means as a theorist, I'm really happy because there is only one length scale that I could possibly be talking about. What's the only length scale left if the length scale of the atom isn't there? It's the wavelength of the light. What's the time scale that it takes for a photon traveling at the speed of light to travel one wavelength? It's 1 over the optical frequency, right? Because, c is equal to f lambda, right? So if I've got a speed of light and I've got an optical frequency, and then the time it takes for my photon to travel one wavelength is 1 over omega naught. And so the time it takes for the environment to relax back into the vacuum is the same time scale that is my big, or my really short time scale, my really big frequency scale. And so as far as the atom is concerned, the environment is effectively always a vacuum as well. So this is all extremely nice, and it means we can start writing down nice equations of motion just for the system density operator, which is the trace over the environment of the kind of state of the whole system. And so what that means is that we're in solid-state physics again. Sometimes people write down a Lindblad master equation as an approximation, okay? Where I have sort of an equation for the density operator that looks sort of something like this. Okay? Where I have something like that, okay, that is often approximate, this type of form, the GKSL Sometimes we call this the Lindblad form. It turns out that Guarini, Kosakowski, and Sudarshan wrote papers about it actually before and also simultaneously to Lindblad. So in recent years in the quantum optics community, we've started saying GKSL. That's a Lindblad master equation in old notation. But as I say, Guarini, Kosakowski, Sudarshan, Lindblad, 1970s, wrote this down to describe open quantum systems. And here, for quantum optic systems, under approximations that are good to 6 orders of magnitude, our small parameter is 10 to the minus 6, okay, we have descriptions in this type of form. This is the normal Hamiltonian evolution of the system. These CMs and again, this could be a whole lecture course, but they are the system operators involved sort of in coupling to sort of Bath operators, okay? So normally, these are the terms that appear in the interaction Hamiltonian with the Bath, and they kind of describe the intrinsic physics that you're sort of thinking about here. So my two-level system, okay, if I'm going to describe just spontaneous decay of a two-level system, I've got one C operator, okay? This looks like sort of minus I over H bar, H rho, if this is my system Hamiltonian, okay, minus this, and now what is my C operator going to be? Well, if you let me define sigma minus as the operator that takes me from the atomic excited state to the ground state, and sigma plus is the operator that takes me from the ground state to the excited state, then these operators are the ones describing the decay. So my Cm, okay, I've only got one of them. This is my C1. There's only one of them. Is my operator taking me from the excited state to the ground state? Okay, why don't I have the one in the opposite direction? Because exciting the system and emitting a photon doesn't conserve energy. Okay, again, big frequency scale associated with that. And so, in fact, what I end up with here is a sigma plus, sigma minus rho, plus rho, sigma plus, sigma minus, minus twice sigma minus rho, sigma plus. Okay, so this is sort of a starting point, and of course there's no sum of m because there is only one m. Now, imagine that I don't just have an excitation of an atom that's stationary, but I now want to include motion in this. What's going to start to happen? Well, my Hamiltonian is going to be something like sort of a p squared divided by 2m. And then I'm going to have this kind of laser excitation, which is my kind of sigma, my omega of x. And this is going to couple the excited state to the ground state and the ground state to the excited state. Okay, and I'm going to have then normally some sort of detuning of the excited state that I'm going to write in an interaction picture or something in quantum optics with a particular frequency choice that we call the rotating frame. It's rotating at the frequency of the laser. And so this is going to be my Hamiltonian. What are my sigma minuses? What are we going to, sigma minus is going to be replaced with in the case that I have motion? Right, so you're right. Okay, in the case that you've got a particle trapped in a harmonic oscillator. So here I'm writing down free space, and so I can't do that, but I'll take exactly the operators that you would normally project onto your harmonic oscillator eigenstates, and then they would give you indeed ladder operators. So fantastic answer, Awana. So in fact, when I have spontaneous emission in the presence of this, so this is now with motion, okay, in fact, my Cm becomes a Ck effectively that I'm going to have to integrate over, and it looks like a sigma minus for my decay. And then I'm going to have something like an e to the minus keg, so this is kind of now the wave number that is effectively associated with the decay from the excited state to the ground state. And then I'm going to have, actually let me write this in terms of unit vectors u, and I'm going to have u dot r, okay? And what this is really doing, this is basically my e to the minus I kx. It's my momentum recoil, okay, coming from the emission of the photon. And if I'm far tuned from the excited state, I can start to describe all of these processes. I'm going to get a momentum kick from the excitation in the omega of x, and I'm going to get another momentum kick from the photon that pushes me out. And in fact, this is the basis for starting to talk about how you move atoms around with light. It's also going to tell you, it's going to be the basis for describing laser cooling. So back in the early 90s, these were the things that people wrote down when they were trying to simulate sort of processes or describe mathematically processes of laser cooling. Now, of course, we have exactly the same types of things with systems coupled to their environments, and with this type of decay and light scattering when you deal with atoms in optical lattices. And this ultimately is the thing that fundamentally, if you're going to trap atoms with light, this type of thing sort of fundamentally limits the coherence time, because there's always going to be the possibility for spontaneous decay of the atom. But now we can write down and derive from first principles under approximations that are good to 7 orders of magnitude, okay, equations for that. And if we do it in a regime where this is far tuned, we can also, in perturbation theory, integrate out the excited state and just look at the motional effects on the atoms of this absorption of a photon and this recoil. And we can write this for many-body systems, and it turns out that although it looks like a little bit of a mess, that the master equation is not so bad, okay? Even in these many-body systems for dealing with these things. Now, if you, who's familiar with second quantized field operator notations? Okay, who's not? If you're not, this is the only thing that you are going to see today other than what I wrote up with the hydrogen atom earlier, where you're going to see these operators, and I'm going to explain physically in a second what this actually does. So what does this look like? I've got this field operator that is psi dagger psi, and so that has to do with the density. What physically does this decoherence, this fundamental decoherence process for atoms and optical lattices look like? What's it doing? If I start with an atom that is delocalized over the lattice, what does this describe? How about I ask a different question? If you walk into a dark room and you want to know where the objects in the room are, what do? You scatter light off them, right? And you look at where the light is, okay? And it turns out that this is exactly what this is doing. If you look closely, okay, this thing here, there's a function f, which turns out to be localized on a scale of the wavelength of the light. Again, the only sort of scale that's left in the problem in describing what's going on here. Okay, and when you integrate out all of the different directions that the photons can be scattered in, what you see is that this master equation is almost diagonal up to this sort of wavelength. So what's happening is scattering light is giving you information about where the atom is. So if it was in a superposition of all sites, you eventually sort of go down to something where the environment, even if you don't measure the photon, kind of sees where the atom is on a scale of the wavelength of light. And so it decoheres these sorts of superpositions. There's another sort of point here, which is that you can, of course, get excitations to higher bands. Okay, and this comes back to Oana's sort of ladder operators. If you have a harmonic trap, there's a possibility that these things will excite you. And again, for the ion trap and neutral atom experts in the audience, of course, there's a Landicki factor in here that tells you what the possibility is of being excited to higher levels. For those of you who are not familiar with the atomic physics of these systems, when I put a particle in a trap, okay, or in a series of traps, and then I find out where it is on a scale of the wavelength, To a certain extent, that's telling me which trap it's in. But if the wavelength is short enough, it might almost kind of give me information about where it is within the trap. And if it was in the ground state and I get information about where it was within the trap, then that's going to put me in a higher oscillator level. So those excitations depend on the ratio of the size of the trap to the wavelength of light. And this is exactly what this comparison is. Okay, but that's the type of thing that we have. The point is, we can do that for basically every mechanism that you have for decoherence and noise in these systems. And in fact, there's a very nice kind of set of things you can look at with cold atoms, where people at different points in time have looked at heating of single particles or heating of multiple particles. And so you can take these systems where we knew what the Hamiltonian dynamics were, and essentially you can include, again, under well-controlled approximations, all dissipative and noise processes. Of course, if you have noise, like in these systems, sort of fluctuations of the parameters and so on, what this will look like is that your Hamiltonian is some h0 plus hn, where this is a noise Hamiltonian that is then perhaps multiplied by some sort of time-varying function, where maybe the time average of this is 0, and the stochastic average of this is 0, but where there's some sort of strength which has some sort of correlation function in time. It might be, for example, something that is delta correlated proportional to t minus t prime. Then you've got white noise, or you might have some colored noise with a different frequency spectrum. The point is that we can add that to the Hamiltonian dynamics if we know what the frequency spectrum of the noise is, and we can measure frequency spectra for noise on lasers and things like that, and then we can put it into our microscopic description of this. In fact, a side note is that if this is delta correlated, then there's a beautiful transformation, which is that if you take the stochastic average, then in fact, this just gives you a time evolution under h0, okay, with then a Lindblad form master equation, or GKSL form master equation, with an hn squared rho plus rho hn squared plus a minus twice of hn rho hn. Where this gamma depends on the prefactor of the correlation function of the noise terms. So in fact, the stochastic average over a white noise term in a Hamiltonian gives you back actually something that you can put into a GKSL form master equation. So that's also nice if you are already trying to time evolve a master equation. Okay, so the point is that for atoms, this goes very well for atoms in tweezer arrays, where we also have to worry about the atomic physics of Rydberg excitations. This goes well for trapped ions. For things like superconducting systems, because these things have also sort of noise sources that come from the ways in which they're coupled to things electrically and the ways in which they're manufactured, sometimes you really need to go out of your way to make measurements and try to characterize what the equivalent description of the noise is. And sometimes you've got to go past these nice Markovian approximations. So this is extremely nice when you've got this frequency scale separation for ions and for neutral atoms. For solid-state devices, you have to go a little bit further. But in AMO quantum simulators, we can actually go and look really microscopically at what the noise does to the evolution of the system. So that's very nice, because when we want to make these comparisons properly between what we can do with, say, an analog quantum simulator and a classical calculation, it's very important also to be able to say where are the imperfections in the analog simulation. Where does this decoherence actually put you in a position where your results are meaningless? To what extent and on what timescales are these noise sources really going to change what you measure in the experiments? And in principle, you can do all of those sorts of things with help from these sorts of calculations. And so imagine now you want to make this comparison. And you want to say, well, where am I going to do a quantum simulation and choose to do an analog quantum simulation rather than a classical calculation? Well, the first thing is that if you're going to make this comparison, it's really important to define the rules of the game, because you could get different answers depending on what you ask. So the rules of the game that I'm going to choose here are, I'm going to be interested in quench dynamics. And I'm going to talk only about a comparison of these things for doing quench dynamics in these kind of complicated regimes that I struggle with classically. Why don't I do ground states? Why do I choose deliberately to not address that question? So if I want to calculate the ground state of an arbitrary Hamiltonian, in general, it is a very complicated thing, not only classically, but also on a digital quantum computer. I'm not an expert in complexity classes, but there is a complexity class, quantum Merlin Arthur, that basically is sort of anything that you could calculate or things that you can implement on a quantum computer. But things that, in general, that you don't know are going to be polynomial time on a quantum computer, but could be exponential. And finding the ground state of an arbitrary Hamiltonian is equivalent, essentially, to doing any arbitrary quantum computation. Okay? And so, from that point of view, in general, these are hard. And even when you try to do just sort of local nearest neighbor models, these things are also complex. And it's a big moving target because people are coming up with new classical techniques all the time. People are coming up with new ways of doing these things quantum mechanically. And so the jury is out. It's very problem specific, and it's a very complicated question that it would involve surveying a lot of different things and coming up with a murky answer that sort of is just, it depends on the problem. Okay? For quench dynamics, we can say something much more concrete, mainly because we know what the challenges are classically for propagating these things. We know what the best available methods are, and so at least we can ask the practical question of, if we compare with the best available classical methods, where can't we calculate something without an exponential cost that at the moment we're not able to pay on a classical computer. So therefore, we're going to do quench dynamics. If I want to be nice to analog systems, it's going to have to be from a state that can be prepared in polynomial time. Okay, so let's just say in short times, and with a Hamiltonian that we know how to implement. Because if we can't satisfy these two things, we shouldn't be trying to do an analog quantum computation. Okay? I am going to want, in the next rule of the game, I am going to want a quantitative solution. And the reason why I choose that is because I want to think about this a little bit like you might think about a problem in a classical computer or on a quantum computer. I want to be able to specify the precision with which I get these things out. And I don't just want to look for robust quantities. So let me be clear, there are a lot of experiments with cold atoms where people have done beautiful things extracting equations of state for strong interacting gases. Beautiful experiments, for example, at MIT and Martin Swearline's group just up the road. Beautiful things at Cambridge and Zoran Hadzabavich's group with looking at out of equilibrium dynamics. These aren't really problems that we're going in and programming and asking for a quantitative solution to that give us a flexible sort of wide range of Hamiltonians. These are beautiful experiments on a particular type of model that we learn a lot about scientifically. But I really want to ask, if I want to program a problem that was of interest at some point in solid state physics, but I can sort of implement here, then what am I going to do? So I want a quantitative solution to something that's of interest beyond quantitative solution of interest beyond those specific experiments. And again, you could argue that's the case for some of the things in Martin Sweerlein's group with strongly interacting gases. What I'm really trying to say there is that this shouldn't be just testing the hardware. This should be something that's of interest to science or to something beyond that. So what we're going to do is we're going to choose a Hubbard model. We're going to think about what happens with information correlation spreading in a Hubbard model. And we're going to take here calculations that we can do with matrix product states. And you can see that after sort of a short time, if we don't have a big enough bond dimension, that the errors that we would have from compared with an exact simulation, they themselves, not only is this exponentially complicated to go further in time accurately, but the errors themselves also blow up exponentially if you don't do that. Okay, the way we've extracted this is we've done the calculation for a much higher bond dimension, pushing the limits of what we can do and comparing to that. And at some point, of course, you can't do that anymore. But this is to just sort of demonstrate where we are. And we're going to take different observables that we might be interested in. So for example, if I was looking at transport dynamics of fermions across a disordered landscape, I'd be interested in the densities. I might be interested in sort of some two-body, four-body off-diagonal correlation functions. And so these are the things that we're taking. Now you could do this with fermionic atoms and optical lattices. In that case, okay, I am ultimately going to be limited by this coupling to the environment and spontaneous emissions, but I should be very careful because there'll only be sort of a finite calibration of my Hamiltonian parameters. There are going to be the terms that we removed at sort of higher orders in perturbation theory when we were deriving the model. There's going to be potential problems in loading atoms, regularly into the same initial state in the lattice. There's going to be noise that we would need to put into the Hamiltonian that comes from, for example, fluctuations of the lattice lasers. And there are going to be these spontaneous emissions that I showed you the master equation for before. So what we actually did is we went and we simulated all of these things and we asked quantitatively what makes the biggest difference in doing these types of things. And what we found was that at short times, errors in the correlation functions that you would extract are dominated by calibration errors. Okay, and this is, of course, really important. And the one lecture at the summer school that I haven't suggested a connection to so far is the one that's happening this afternoon, where Robert's going to tell us about learning states and Hamiltonians and things like that. Well, Hamiltonian learning is also a really interesting answer to the question of how do I check that I've really calibrated my Hamiltonian as well as I hope I have. And given that in these analog quantum simulators, calibration errors will dominate the errors in the quantities you extract at short times, that becomes very important, okay? So that sort of from this analog perspective really motivates the connections to what we'll hear about this afternoon, and I'm looking forward to that very much. And then at long times, eventually, there's a timescale in which effectively the coherent dynamics get cut off by decoherence from the spontaneous emissions. And so we can go and we can make these quantitative comparisons and we can ask, how do these things grow? How do they spread? There's a beautiful thing, which is also seen in Trotter discussions, also in Andrew Charles's group, and various other people think about these things associated with an Institute for Robust Quantum Simulation. But essentially, if you get a whole lot of local calibration errors, the effects of those across the rest of the system are at short times limited by this light cone for the propagation of correlation. So this actually limits the worst effects up to the point that you get to an evolution timescale equivalent to the system size, that limits those effects at short times. And so at some point, it means that if you have calibration to a particular level, you can fairly reliably extract correlation functions out to a given time. And people always ask why those lines are oscillating. What we've got here is we've got quantities that are oscillating in time, and the oscillation frequency depends on the Hamiltonian parameters. And now what we're doing here is we're sampling from those Hamiltonian parameters to understand the effects of the calibration errors. So we're averaging over different oscillation frequencies for quantities that are oscillating in time. And then we're subtracting the expected value from the average of those things. And of course, whenever you average over something that's oscillating with different oscillation frequencies, you get something that's oscillating. Okay, so that's the reason why those things are oscillating. We can then also simulate using matrix product states in 1D and actually quantum trajectories methods for these master equations for light scattering. And we can understand how the decoherence affects these things, and effectively at some time that's going to cut off the calculations. So in some sense, what you're left with is the following kind of summary. That for things, with these kind of rules, and deliberately going into regimes that are going to be hard for the classical calculations, okay, where we're generating a lot of entanglement, at some point, the errors in the classical calculations, if you don't make uncontrolled approximations, will end up growing with all of our current best methods exponentially. And before that, you should be doing the classical calculations. Okay? After that, what you might want to do is a digital quantum computation using the algorithms that Dee was telling us about yesterday. And of course, if you have the resources, then that is very nice. And of course, what that fault-tolerant machine will do is not only give you access to controllable precision, because if you add more layers of error correction, you can get more and more precise logical operations, and also it will allow you to go to a much wider range of Hamiltonians that you can specify and implement, as we heard yesterday, as opposed to just having access to things that we can build or that we're close to building in experiments. In the meantime, the challenge of this yellow line I'll come to in a second. In the meantime, these analog quantum simulators, okay, will give you quantitatively robust results that can go into regimes now with current experiments that are beyond what we can calculate classically. At some point, there's a cutoff that comes from decoherence that we can't avoid, okay? But those are at somewhat longer times then we need to reach these regimes where at the moment we can't calculate these things classically. And so that's really where we are with cold atoms and optical lattices at the moment. And we have quantitative bounds on these errors from these sorts of error budgets, which I think is really fun. These yellow lines, of course, is ideally what you would like to have for generic models. But the challenge is the question, what type of resources do we need, even to get that yellow line to this level of the red line. And so we estimated this, and it's something I should talk with Dee about actually, and see whether there are any sort of modern insights that might slightly change these numbers. We did these calculations in 2022 together with Natalie Pearson and with Matthias Troyer and a range of other co-authors that gave input on various different things, including Stuart Flanagan, who did these analog system calculations. And essentially what we asked was, what is the least expensive method that will give us simulations as accurate as the analog machines are today? Now that doesn't require the best algorithms that Dee was talking about, because what you want to do, you want to say, I'm happy with quite a big error, I want to have the fewest possible gates. So we were optimizing for something different than what most people were doing. But still, the kind of conclusion was You can't do it without fault tolerance because you would need sort of, gate errors of the order of sort of 10 to the minus 5 or 10 to the minus 6 in order to match in a trotter evolution at fourth order what you have in analog simulators right now. And what you found was that effectively you needed of the order of 500,000 to 1 million logical gate operations in order to look at a Hubbard model on a 10 by 10 grid, with the same precision that we can look at it up to about 10 tunneling times in analog experiments today. So I realize that we're a little bit short of time, so I'm not going to talk much about fast scrambling, but we can talk about it over lunch if some people would like. We have been playing with some fun ideas, trying to think about how the sort of moving of atoms in tweezer arrays can let you generate longer range couplings. And we thought about sort of these hypercube graphs, which you saw have been realized now in this paper in Mish's group, also that he talked about extensively on Friday, and where we can scramble actually to this page curve that I was telling you about. Really check the errors with respect to that on timescales that only grow logarithmically with the system size. And so this is fun, and we're sort of thinking about ways we might use that to generate and code and make use of entangled states in the future. But it allows you, at least in a discrete sense, to get up to these types of these logarithmic light cones kind of for spreading of information and scrambling that I mentioned earlier. Of course, I've already kind of told you the answer to this one. Is open quantum systems dynamics really bad? Well, of course not. And you can look at interesting many-body physics, and you can control non-Markovian dynamics. So we have a lot of fun with that. But let me kind of finish, basically, with my sort of overall kind of statement that we're obviously very interested in digital quantum computing. Within my group, also, we have a lot of people working on digital quantum computing and thinking about how to implement better gates in neutral atoms, thinking about applications of digital quantum computing. And I strongly subscribe to the same things, to all the things that Misha was saying at the end on Friday about the importance of co-design, really understanding the application, the ways in which to encode that into algorithms, and the error correction schemes that you will need to suppress errors in these cases. I think that goes also across, back to the analog machines, and maybe most excitingly to this idea of sort of having sort of hybrid analog and digital machines. There was a beautiful paper by Google a little bit ago, and a lot of these things coming out of tweezer array experiments are also in the same spirit, that you have some sort of digital gate operations combined often with a little bit of analog evolution. And I think there are lots of interesting things you can do, studying out of equilibrium dynamics, thinking about building states for programmable quantum metrology, and I think that there can be lots of fun in that. But the other thing I should emphasize is that, partly because of this combination with digital and partly because of the fact that it's easier on an analog machine where you can implement a Hamiltonian and just evolve this rather than having to program this as a series of trotter evolutions or the more interesting, sophisticated algorithms that Dee showed us yesterday. I think that for a long time, there are going to be advantages to having analog quantum simulators and to wherever you can using this analog evolution. And it's not going to give you arbitrary precision, generally, and it's not going to give you arbitrary access to models, but it gives you access to these things with so many fewer resources that I think it's going to be a long time scale of the order of decades in the future, where you're still going to see the relevance of analog devices. And the perspective of that in the classical world is that we still see people using wind tunnels and water tunnels to look at aerodynamics and hydrodynamics, despite the fact that we have exascale supercomputers. Some problems are just easier to build and study in the lab in an analog fashion. And it's even better if you can combine it with digital. So, thank you.
We'll just quickly, just one or two questions, and then we'll break for lunch.
Oh, see ya.
So the Question is probably pretty quick. What kind of like physical system that you would expect to see more non-Markovian dynamics?
So, really good question. What sort of physical systems do you see non-Markovian dynamics in? The short answer is anything that doesn't satisfy these nice separations of frequency scales, and that's a lot of things in the solid state very naturally, where you've got spins coupled into spins on very similar energy scales. The solid state physics, non-Markovian is kind of the norm, actually. In these AMO systems, we're seeing now a lot, for example, atoms in multimode cavities, for example, where in principle, the decay of the cavity is beautifully Markovian. But if you've got many cavity modes and many atoms, it can be unwieldy to try to calculate the whole thing. And if you're interested in the dynamics of the atoms, you might want to actually trace out the cavity modes. But there, if the atoms are strongly coupled to the cavity modes, that will naturally become non-Markovian. What we've been doing a lot of in our groups thinking about those sorts of AMO systems where you really want to trace out part that is still strongly coupled. And there are good fun sort of approaches you can use there. And quantum transport, which is again ubiquitous in solid state physics, but you now see with cold atoms and optical potentials, is another place where you get very naturally non-Markovian dynamics because you don't have the same separation of scales in the coupling of the system with the environment.
Thanks for a great lecture. From the first part, closed system, we heard about like what kind of physics problems we can look at, like thermalisation and those stuffs. For open quantum systems, what like big like physics signatures phenomenon do you would like to see? Yeah.
So I guess that there are a number of ways to answer that. Quantum transport systems and access to transport phenomena, I think, would be something that I think is particularly interesting. In AMO systems, I really like some of the experiments that were done in Zurich and Lausanne over the last years by Tilman Esslinger's group and Jean-Philippe Brantu's group. And so again, heading into kind of sort of transport dynamics, I think is interesting. I think studying open quantum system dynamics is also interesting simply purely from the control perspective. Can we do more things, driving systems into sort of chosen many-body states? And can we uncover other sort of phenomena? People have talked a lot about these measurement-induced phase transitions, for example, which I think have got very exciting for us as theorists.
Which phase transition?
But the question is whether you could take some of those things and with sort of measurement and feedback, maybe turn those into, interesting types of dissipative many-body phase transitions. And there are condensed matter and sort of field theory people thinking about universality in certain types of open quantum system dynamics. Sebastian Diehl in Cologne does a number of things along these directions, which I think is also, from a physicist's point of view, a really interesting direction. Quantum optics, with my quantum optics hat on, I'd love to see more many-body laser cooling. We want an interesting many-body state. We want a solution to a quantum problem. Can we dissipatively drive into it? Because if you can dissipatively drive into something, it's normally more robust to noise as well than Hamiltonian dynamics are. So those are the sorts of things, but I think it's a big area and there are many opportunities.
Thank you.